This next example, the part that's wrong, the part that makes it so we can't just apply the fundamental theorem of calculus right away, is that we're supposed to have an upper limit that's a variable and a lower limit that's a constant. Here we have a lower limit that's a variable that matches the variable that I'm differentiating with respect to, and an upper limit that's a constant. Well, this one, it's easy enough to fix because if I want to just switch those limits, I can do that as long as I use the opposite of the integral. So this one, if I want to take the derivative of that integral, that's the same as the derivative with respect to time, with respect to t, of the opposite of the integral with the limit switch. So 5 and t, now we're up here. This is 3p sine p dp. And that's okay, that's p is just another variable. As long as the only variable inside my integrand is p, then I'm going to be fine. There's a big bracket. So that's going to be, now I'm taking the derivative with respect to time of this integral. The lower limit is a constant, the upper limit is the variable t. That negative is just going to factor out to the front, and I'm going to get the opposite of 3t sine t. That's the integrand, which was 3p sine p, with all the p's switched to t's, because t is my upper limit. Okay, and here's the last example. This is another possible problem with those three rules that we can overcome. Here I'm trying to take the derivative of an integral, and both the lower and the upper limit of that integral are functions of the variable that I'm differentiating with respect to. So I don't have a constant at either as either limit. So what I'm going to do here is split that integral into two parts. Remember, to integrate from 2x to x squared is the same as integrating from 2x to 0 and then adding the integral from 0 to x squared. So that's my plan here. I'm going to rewrite that integral. You just pick any constant you want. 0 might be the easiest one to use, but it doesn't actually matter. And even if you don't think 0 is between x squared and 2x, it doesn't matter if that constant is actually in between. That rule for adding integrals still works. So here's what happens is I've split up my integral. Instead of integrating from 2x to x squared, I'm integrating from 2x to 0 and 0 to 2x. Notice here in this slide, maybe that's written in the opposite order you might have expected, but I'm just adding, so the order doesn't matter. Now, the first integral here, the integral from 0 to x squared, that's all set. There's no problem with that integral. I'm going to be able to take that derivative. Here, for this integral, I have that problem where the lower limit is the function of the variable and the upper limit is the constant. So I'm going to do the trick where I switch the limits by taking the opposite. That's how this addition sign turns into subtraction. And now I'm going to have sort of two separate integrals that I'm differentiating. I'm going to have to use the chain rule for both, because here the upper limit is x squared instead of just x. So I'm going to have my integrand 1 over 2 plus e to the t. I'm going to replace the t's with x squareds, and then multiply by the derivative of that upper limit, which is 2x. Then I have the subtraction sign. You see it comes straight down. I'm going to here replace the t's with 2x, and then multiply by the derivative of the upper limit. So 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. So that was one part of the fundamental theorem of calculus. You can take the derivative of an integral, as long as you meet all the rules, and the derivative will sort of undo the integral and leave you behind whatever function was inside the integral. So you might like to think of that as derivatives undo integrals. Here, the other part of the fundamental theorem of calculus, we've actually already learned it. Essentially says that integrals undo derivatives. So we said in the last section, 5.3, that if you could think of any antiderivative for your integrand, so in this case, if I could think of any antiderivative for f of x, call it capital F, then the integral from a to b of little f is capital F of b minus capital F of a. So actually I already practiced this a little bit in section 5.3. This is a good example here because when you look at this problem, you might think to yourself, I don't actually know what 3x, I can't think of a function off the top of my head whose antiderivative No. Whose derivative is 3x plus 1 squared. Well, part of that problem is because 3x plus 1 squared is a pretty complicated expression. So this is actually sort of a trick problem, a little bit of a trick. You won't have much luck answering this until you think about rewriting that integral into a function whose antiderivative you can think of. So for me, 3x plus 1 squared, let's multiply that out. So that's 3x plus 1 times 3x plus 1. That makes 9x squared plus 6x plus 1 dx, right? And then hold on. So this is my new integral. I need the integral from 0 to 1 of 9x squared plus 6x plus 1. So this, you got lots of it practice in class today. I'm going to have to think of an antiderivative of 9x squared plus 6x plus 1. So that looks like this. I'm going to take the exponent on x and increase it by 1 and divide by the new exponent. Six x to the first, I'm going to change to 6x squared and divide by the new exponent. Plus 1. The antiderivative of 1 is x. And then some of you asked, it's a really good question, why don't I have to figure out what c is? And it's because that second part of the fundamental theorem of calculus says this works, this trick of evaluating capital F of b minus capital F of a works for any antiderivative, not just the one correct antiderivative. So you can go ahead and assume, when you're using an antiderivative to evaluate an integral, assume that you have the correct antiderivative, assume that c is 0 in this case. So from 0 to 1. So I'm going to clean this up a little bit. That's 9x cubed over 3 is 3x cubed plus 6 divided by 2 is 3x squared plus x, and I'm going to evaluate from 0 to 1. So what does that mean to do? It means I'm going to plug in 1 for x, so that's going to be 3 times 1 cubed plus 3 times 1 squared plus 1. And I'm going to subtract what I get when I plug in 0. So make sure this second part that you evaluate, the part after the subtraction sign, goes in parentheses. 3 times 0 cubed plus 3 times 0 squared plus 1. So that's 3 plus 3 plus 1 minus 1. Final answer is 6. Okay, I'm not overstating this, in my personal opinion, when I say that this next problem we're going to do, it's the most important example in all of Chapter 5. Sort of your ability to answer like the last 20 or 30% of the questions on the AP Calculus exam all come down to understanding what's about to happen. So before we do that example, we're going to do a little bit of practice. Just make sure you can answer these questions. This is stuff we've just learned in Chapter 5 so far. What is the integral from 3 to 3 of tangent t dt? Well, I hope you know the answer is 0 because the upper and lower limit match. So we're describing an area under a curve that has 0 width, so it must have 0 area. And then here, the derivative with respect to x of the integral from 3 to x of tangent t dt. Well, we learned the fundamental theorem of calculus tells us that derivatives undo integrals, and we're just left with a variable change that's going to be the tangent of x. So next video, we're going to do this most important example.